Okay, so what we're going to talk about today is recursive sequences. And this is a type of sequence that very frequently, to prove something about a recursive sequence, very frequently it's appropriate to use induction. So what's a recursive sequence? Well, recursion generally means a function that depends on its previous terms, a function that can be evaluated by evaluating the previous term. For example, so what's an example of a recursive sequence, just to start us off? Something like this: an equals to an minus 1 plus an minus 2. So what I'm saying is that I have a sequence of numbers a1, a2, a3, and so on. And what I can do is, to determine each term, to determine the third term, for example, I have to take the sum of the previous two terms. That's what recursion means. Recursion means that to evaluate the nth term, you need to make reference to the previous several terms, in this case, the previous two terms. Now, the problem with this sequence, does anybody notice what the problem is? That I've made a little bit of an error here on purpose. Maybe. What's missing from this definition of a sequence? Yep, exactly, Michael says. A1 and A2 don't have any values. I tell you how to obtain each term from the previous two terms, but what about A2? There's no two terms before it. There's only one term before it. And even worse, how about A1? There's no two terms before. There's no terms before A1, right? So this expression that I wrote here, an equals an minus 1 plus an minus 2, only works if n is greater than or equal 3. Because otherwise I can't, if n was 1, I can't subtract 1 from n. I'd get 0, and that's not a natural number. So I also have to specify the base case, just like induction. Recursion and induction go hand in hand. I have to specify the base case. I have to tell you what the first two values are. After I give you the first two values, you can use the recursive formula to get any other value, okay? So for example, I could have told you A1 was 1 and A2 was also 1, just whatever. And then the sequence I'm going to get, the first two terms are 1, 1, 1. Next term is obtained by adding the previous two terms. So 1 plus 1 is 2. The next term would be obtained by adding the previous two terms. So 1 plus 2 is 3. The next term after that would be obtained by adding the previous two terms. So 2 plus 3 is 5. And you would keep doing this by adding the previous two terms. And this is a very famous sequence called the Fibonacci sequence that mathematicians love. So in any math class you take, I bet you at least one point, the professor is going to take liberties to somehow bring up the Fibonacci sequence. You're going to see it a lot, probably. Okie dokie. So if you understand this little definition of a recursive sequence, this was an example of this is the Fibonacci sequence. And it's a very common example of a recursive sequence. What I want to do is show a couple inductive technique you can use to prove that a recursive sequence is bounded, or to prove that a recursive sequence has a closed form. Like here, if I wanted to ask you what's A69 or maybe A73, right? If I wanted to ask you for some random value of A, or a random value in the sequence, what's A73, you'd have to calculate the first 72 terms before you can get there, right? And that's really, really messy. It would be a lot nicer if there's a general formula that you could just plug 73 into and get the value of A, right? That would be a closed form. But we don't have a closed form. So that's the type of thing I want to talk about today. Okay. Okie dokie. So here's our first polling question. Here's a recursive sequence. An plus 1 is an divided by n. So you can get the next term in the sequence by taking the last term of the sequence and dividing by n. And of course, to specify a recursive sequence, I have to specify the base case. And so we say a1 equals 3. And I only need one base case in this for this sequence, because this n plus 1 term only makes reference to one previous term. So you only need one base case, in short. Okay, so where's that polling question? Here it is. How do you find the fourth term in this sequence? How do you find the very fourth term in this sequence? Okay, 5, 4, 3, 2, 1, and I'm ending the poll now. Okie dokie. So a lot of people seeing B. Okay, let's see if that's right. Let's see if B is correct. So what would I do? I know A1 is 3. So by that recursive formula, A2 would be A1 divided by what? Divided by 2? Or divided by 1? Ooh, is it A1 divided by 2 or A1 divided by 1? Which is it? It's 1, right? See, the index of this numerator has to match this n. You have to pay close attention to this formula. Play a little bit of matching here. So it's not a A1 over 2, it's A1 over 1, which is just 3. Okay, and then I can get A3, and I get A2 over 2, which is 3 over 2. And then I want A4, which is A3 over 3, which is 3 over 2 over 3, 3 over 2 over 3. Let's write it like that. And that's 1 over 2. So the answer is B, 1 over 2. And you guys got it? How about A9? How would I get that? And you could just keep going up this ladder the way I was doing recursively. But that might be okay for 9 because you have the patience for it. But what if I asked you I don't know, 54? How would you get that? That's where a closed form is going to come in. And you might want to try to find a pattern here. Is there a good pattern? Is there a good pattern? Let's see. If I want A5, I can write that as A4 over 4. And A4 I know is A3 over 3. So this is A3 over 3. And that's A2. A3 is A2 over 2. And then A2 is A1 over 1. See? It looks like I'm just multiplying all these denominators together, and I have A1 on the top, and A1 I know is 3. So I can write this last bit as just 3 over, and that on the denominator is 4 factorial. See? So you can kind of think, oh, that kind of makes sense, right? I'm just multiplying a new n every time, and then I get the previous case. The previous case multiplies n minus 1 into the denominator, and then I get the previous case before that, and I just keep going down. Eventually, all the denominators is going to have all possible n's in it, and then the numerator is just going to be the first base case, which we said was 3. So in general, you have a closed form for this sequence that an, it appears to me, is going to be 3 divided by n minus 1 factorial. Okay, that's not so bad. And the argument I gave was just, I just said, oh, it looks like a pattern. You can generalize, right? But how do you actually prove that this is the closed form? This is the proof by induction. So you can prove this by induction. And maybe if we have time, I'll get back to that. But for now, let's move on. But this is a good exercise for you. Given this sequence with this base case and this recursive formula, prove by induction that an equals 3 over n minus 1 factorial. Okay. So if I ask you A9, I don't need to calculate A1, A2, A3 all the way up to A8. I don't need to calculate all those terms. I can just plug 9 into this formula. So for example, I could just do A9 equals 3 over 9 minus 1 factorial, so 8 factorial. And I don't want to calculate that but I can just leave it like that as exact form. See? Closed form means a formula. Closed form EULA. It's a formula that you can use to get any term in the sequence. Okay. Any questions about this? No questions. Okay, good. So let's go to the next polling question. Oh, there's one question in the chat. If someone else can answer that one, explain what we just did, that would be helpful. Okay, here's another polling question. And this is a test from the textbook, just to make sure you're reading it. Here's example 4.4.2. And what they did in that example is they proved this. They had a recursive sequence, including a base case. And then it was exactly a question of the form that I just suggested a second ago. Prove that AN has this closed form. So this was a closed form example. Okay. The question was, prove that AN has this closed form. And then they gave a proof by induction. And in that proof by induction, how would you put the induction hypothesis? That's basically what the question asked. What's the induction hypothesis in this proof? Okay, what's the induction hypothesis? 5, 4, 3, 2, 1. I'm ending the poll. There's always a couple stragglers who never get their vote in. I don't know why that is, but okay. Question C, or sorry, answer C is what you guys are saying. Yep, that would be good, right? Because when you set up this proof by induction, you assume that the statement is true for some k, and so what you do is you replace n by k, and you get this statement. Well, that's all there is to it. It's pretty straightforward. So you're right. C was definitely correct. Okay, because if it was this isn't the right thing I'm trying to prove. This B here, I'm not trying to prove that AN plus 1 equals 5AN plus 1. Right? That's what I'm given. That's the formula I'm given. I'm not trying to prove that one. Okay, so that's why it's not B. And people are trying to say, why is it not D though? Why isn't it D? Right? This is the induction conclusion. This D here is the induction conclusion. Because one way you could reason it out is, well, look, this is the statement I'm trying to prove here, right? This statement that I'm highlighting in green. So if this is the statement I'm trying to prove, why don't we call that Pn? Remember, induction is like, let's prove P of n for all n. And so induction hypothesis is always like this. The induction hypothesis, induction step, let me say, induction step is always like this. Prove that P of k implies P of k plus 1. And so what you do is you assume P of k for some k, and you prove this here, P of k plus 1. This part that you're assuming, that's the induction hypothesis, right? So P of k, that means I take P of n and I replace n by k. And if you do that, you get C. If you replace n by k plus 1 in this statement, if you replace n by k plus 1, you're going to get this statement. But that's not the induction hypothesis. The induction hypothesis is P of k, not P of k plus 1. So that's why it's not D. D is the induction conclusion, not the induction hypothesis. Hypothesis, conclusion, down here. Okay? Clear now? How would you go on to prove this? Well, this example is literally from the textbook. So I encourage you to finish the readings before class, or if you still are stuck on it, you could try reading what's in the textbook because the proof is completely written down there. And if you're still stuck on it after reading it, then you can let me know. The proof is completely in the textbook. Example 4.4.2. Okay. You have to do the readings before class, guys. Before class. Before class. I know you don't do it, but you're supposed to do it. And I'm going to pretend that you did it forever. So every time you come to class, I'm going to do stuff that is dependent on what you read in the textbook, whether or not you actually read it. I'm still going to do it. Okay. In fact, I think I spent a lot of time I spent a lot of time talking about things that were in the textbook when I really shouldn't, and then we end up falling behind. Okay, let's do it. One more poll question here. So I have a sequence Bn now, and Bn, I'm not telling you what the recursive formula is. I'm not telling you anything about Bn except what the 15th term is and what the 17th term is. Which one of the recursive sequences here can Bn satisfy? Okay, this is kind of a tricky one. But think about this for a bit. I might have to give you a lot of time for it. But which one of these formulas could Bn possibly satisfy, considering this condition here, that B15 is 3, the 15th term the sequence is 3, and the 17th term in the sequence is 10. 4, 3, 2, 1. That's not a second, but that's okay. All right, I'm ending the poll now. To-do. Okay, so people are getting D. Nice. This is kind of a tricky question. Does anyone want to explain their answer? Does anybody want to try to explain how you got D there? Elimination, right? Elimination's good, but then how did you conclude D eventually? I guess you said, oh, it's not A, B, C, but how do you know it could be C or D? Yeah, Mohadis, if you want to unmute and tell me what you got.
Okay, so I got D, and the reason I got D is actually I checked them all in order from A, B, C, and D.
Yeah.
So I know that my B15 is 3 and my B17 is 10. So my thought process is forget about B's 1 to 14, just do B15. And I
Yeah.
can like make an intermediate step, find out B16 and then B17.
Yeah.
So
Exactly. Yeah.
A, B, n plus 1 equals 2bn. That means I just have to double this. So
Yeah.
that would become 3, then 6. Like B15 is 3, then B16 would be 6.
Mm-hmm.
And B17 is 12, which eliminates A because it doesn't satisfy B17.
I see. Okay, so hold on. Let me get what you're saying. Let me erase this solution thing. Maybe I'll just write the solution in this gap here, right? If I want B17 here, well, to get B17, I would have to double B16. And to
Yeah.
get B16, I would have to double B15.
Yeah.
So let's get this straight. Thanks for your answer, Mohadis. That I think you're definitely correct. B17, right? I know that's 10. That's what I'm given. And then B15, I know that's 3. So I've got 2 times 2 times 3 over here. That's 4 times 3, that's 12. So I see 10 equals 12, and this couldn't possibly be the answer, right? So it can't be A. See? And then you can do some similar logic for this, and I'll do it quick. 10 would be B17. B17 would be B16 plus 2, which would be B15 plus 2 plus 2. So plus 4, which is 3 plus 4, which is 7. And now I can say 10 equals 7. That doesn't work. So this formula couldn't possibly be it. Okay. Now, these formulas are fairly simple. In the first one, you're just doubling, and the second one, you're just adding 2. But in C, you've got a mixture of doubling and adding 2. In each of the even and odd cases, you've got something different going on. So let's test. Let's test what's going on. Let's do the same logic. So I know B17, well, that's obtained from the previous term by doing what? By doubling or by adding 2? How do I do that? Anybody can answer?
That one would be adding 2 because to get to B17, you'd have to add 2 to B16. You'd get it from B16, and that would be adding 2 because 16 is even.
Exactly, right? To get the next term in the sequence, the previous term, you add 2 if the previous term's an even index, and you multiply by 2 if the previous term is an odd index. So the previous term before 17 is even, it's 16. So you add 2. And then to get the term before that, it would be B15, which is an odd index. So I multiply that, sorry, B16 is 2B15 plus 2, right? So now let's test. B17 is 10. B15 is 2. So I've got 2 times 3 which is 6 plus 2 is 8. So I've got 10 equals 8, and I know it couldn't possibly be C because of that. And then you could check D, but we don't need to by elimination. That's an efficient way to get through it. Okay. Getting it? For D, I'm not, I could check D. And okay, fine, let's do that. Let's see what happens. So B17 would be, well, I reversed these steps from part C. So since 16 is even, I'm going to do 2B16. And then I replace B16 with B15 plus 2. Okay, and let's check. B17 is supposed to be 10. B15 is supposed to be 3. So I have 2 times 3 plus 2, which is 2 times 5, which is 10. So this seems to work. This seems to be the only one that actually has that these two terms actually satisfy the values. Okay. Okay, question. And then we'll get to the exercise. Burgess, you had a question? Why is B16 equal to B15 plus 2? Okay, right? B16 is an even index, right? B16 is an even index. And to get an even index, that means the index before it is odd. And so if the index before is odd, then I have to add 2. So I add B15 to 2, right? It's a bit of a trick question. I know a lot of people are going to say, oh, 17 is odd, so I should be in this case, right? No. B17, sure, 17 is odd, but you're looking at the previous term. The previous term is B16. 16 is even. Okay? Quick math. You guys good? Everyone's good? Everyone's good to go? Nice. We have about 18 minutes left. That's enough time to do a couple exercises. Ta-da! So these are a couple proofs for you. So now the meat of the stuff. So here's a sequence Cn, and Cn plus 1 can be obtained from Cn by squaring Cn and adding 1/4. Okay? And the base case is C1 equals 1/4. So the question is, prove that Cn is always between 0 and 1/2 for all n. Okay, that's the question. Prove this. And then there's another question very similar. Here's another recursive sequence. The form is a lot simpler. It's just to get the next term, you multiply by 6 and add 5. Okay, prove that when this process results in a number divisible by 6, no matter what n is. Okay, so here's the question for you, and I will take it up shortly. Okie dokie, let's take up this problem here. So you have a recursive sequence. I'll do the question 2 next time. But yeah, you have a recursive sequence defined by this recursive equation, and I have to prove that Cn is between 0 and 1/2 inclusive. Okay, so let's take that one up. So solution. And it's off the screen now, but let me just write it again. Well, actually, in fact, let me copy this information down so that we can see it. I'll just put it right over here. And the solution starts like this. We must prove that Cn is between 0 and 1/2. So that means I have to prove that Cn is bigger than 0 and Cn is less than 1/2. So I have 2 things to prove in a sense, but I can prove them at once. Watch. Okay, so by induction. Let's say by induction on n. So when I set up an inductive proof, first thing is base case. And I want for all natural numbers n. So in this case, I do n equals 1, in which case I know C1 is 1/4. And that's definitely between 0 and 1/2. So I'm going to use interval notation to this as a shorthand. Okay. All right. Base case and then induction step. Let me not just say, assume that P of K is true. That's kind of weird. Let's not say it like that. Let's say the same thing in a more logical way. Let's just say it like this. Suppose we've already proven P of K. We've proven that CK is between 0 and 1/2 for some K. Okay, for example, I've already proven it for k equals 1. So what I'm going to do is show now that I can deduce c of k plus 1. We will show c of k plus 1 is between 0 and a half. Okay, so okay, to show that it's positive, to show that c of k plus 1 is positive, so let me say it like this. C of k, well, yeah, let's just say it like this. C of k plus 1 equals c of k squared plus a quarter, which is a square plus a quarter. So this is definitely bigger than a quarter, which is bigger than 0. So that tells me that c of k plus 1 is positive. So it's probably better to put a little sentence in the middle here. I should have said, to see that c of k plus 1 is positive, observe this, right? Just announcing what I'm proving so that the TA doesn't get confused, or the reader, who is usually the TA. And now to see, oh, sorry, that's not a full sentence. I should have said to see that c of k plus 1 is positive. Sorry, that wasn't a full sentence. Okay. Next, let's say to see that c of k plus 1 is less than a half, what do you do? Does anyone want to give me a little tip for that? Start me off. How do I prove this one? Because this is really the meat of the proof. How are you going to start me off? Sum of squares. Interesting. What are you saying, Burgess? That's very cryptic what you're saying. Find closed form. That, okay, if you did that, that would be badass and it would be overkill for sure. Let's just use the recursive form. You definitely don't need to use a closed form. In fact, I don't even know what a closed form is for this one. Okay. Let's do like this. C of k plus 1 is c of k squared plus a quarter. And what do I assume? I assume that I've already proven that c of k itself is less than a half. So why don't we use that? I know that this bit here is less than a half before I square it. Right? So I know this entire expression, I can replace c of k with half and I'll get something bigger. So I have a half squared plus a quarter. And so let's work that out. I get a quarter plus a quarter, which is an eighth. Or sorry, not an eighth, it's a half. What am I talking about? It's a half. And that's it. C of k plus 1 is less than a half. There's my less than sign in the middle there. So that's good. So you can put a happy face. So therefore, we've shown that c of k plus 1 is between 0 and a half, which is what I was trying to show here. And now I say by induction, ck is between 0 and a half. Sorry, cn is between 0 and a half for all n. Okay, and that's the proof. Okay, and then I know I had another question here. You should definitely try doing this one on your own. And then if you get stuck on it, don't forget about Discord. Okay, so I'll take up that next question on Friday probably, okay? So that's it for this induction question.